let's dive right into molecular structure and the strengths of acids and bases. I'm mostly talking about organic acids and bases here, but this still applies a bit to the inorganic stuff we've been working with, sulfuric acid, phosphoric acid. The Lewis definition is what we're focusing on here because it's about the concentration of electrons in places. So, remember, an acid is an electron pair acceptor and a base is an electron pair donor. So anything that withdraws electrons from a place will make it a stronger acid and a weaker base. Anything that donates electrons will do the opposite, make a weaker acid and a stronger base. Meaning that if you have a region A that withdraws electrons from region B toward itself, then region B will be a stronger acid. And anything that donates electrons, anything that increases electron density is going to make a stronger base. So we look here, for example, a nice instructive example, sulfuric and sulfurous acid, H2SO4, H2SO3, top and bottom respectively. Now they each have two OH groups there, but sulfuric acid also has two double bonded oxygens. Sulfurous acid only has one double bonded oxygen. And those oxygens are very electronegative. They are electron withdrawing groups. So they pull hard on those electrons, and they pull on the oxygens, on the other two oxygens, through the sulfur. Whereas down on sulfurous acid, there's only the one oxygen pulling electrons toward itself. So sulfuric acid is a strong acid, sulfurous acid is a weak acid. And then we can come over here and look at these organic molecules. Okay, you have this oxygen anion up here on this butane that has a lot of electron density there. Okay, you're going to have a very basic character in that molecule. And down at the bottom you have what's known as tautomerization. It's a form of isomerization. It's a reaction within a molecule. And this can influence the density of electrons. Sometimes you have that double bonded oxygen, sometimes you have the double bond within the chain of the molecule. And that movement, that shift of electron density can influence acidity and basicity of that molecule. So, all told, electron density, electron withdrawing, electron donation, nucleophile, electrophile, these things are all sort of part of the language of chemistry and how these molecules behave, in terms of being acidic or basic. So I think that's enough said about that. Let's go ahead and move on. And next up we have resonance. Okay, remember, resonance is a thing that makes molecules happy. Okay? I note here the carboxylic acids. We're also going to talk about phenol. Okay, so first, carboxylic acid, specifically acetic acid. And I'm comparing it here to ethanol because they're very, very similar. The difference between them is the double bonded oxygen. That's it. And acetic acid up top is a weak acid. Ethanol down bottom is not a weak acid. Its Ka is something like 10 to the negative 15th. Okay? That is not an acidic proton. So why is that? Well, resonance. When you pop off that acidic proton up there on acetic acid, you get these two forms. Notice they look pretty much exactly the same. One oxygen is double bonded, the other oxygen is single bonded with a negative ion. And it just sort of, those two forms exist at the same time. That's resonance. And resonance makes molecules happy. So because all the carboxylic acids have that carbon double bonded to oxygen, single bonded to OH, they all have access to that resonance. That's why they're called carboxylic acids. They're all weak acids. Ethanol just doesn't have that. Moving on, we have phenol. remembered this from class. You know, a benzene ring with a hydroxide group on it. Remember, a benzene ring is those 3 double bonds. Okay, they can be 1 to 2, 3 to 4, and 5 to 6, or they can be 6 to 1, 2 to 3, 4 to 5. You know, that's why we draw it as the ring rather than the circle in the middle of the ring, rather than as just the 3 bonds. But when you remove the acidic proton up there, you get this huge mess of resonance because of those double bonds. So you can have the negative charge there on the oxygen, or you can have it on carbon 2 or carbon 4 or carbon 6, with all these double bonds flipping around all over the place. And so phenol is, oh dear, that says weak base. It should say weak acid. I am very much out of it. I do apologize for that. So phenol is a weak acid in a way that, again, most alcohols are not. All right, so just be aware when you see double bonds, or even triple bonds sometimes, but mostly double bonds. When you see double bonds, you have the possibility of a resonance of some kind, and that can have a significant impact on the behavior of these molecules. And now, real quick, I would like just to briefly mention a special class of chemicals known as the amino acids. You may have heard of these, but now you might recognize a bit more about them. They are a class of compounds that look like this, mostly. There's some variation here. But you have an amine group at one end, or an amino group on one side, and then you have a carbon bound to R. And in this case, R, there's 20 different things R could be, but it's this R that gives each of these amino acids its personality, makes them different from one another. And then you have the carboxylic acid over here at the other end. And what makes these guys neat is that you can add a second amino acid, and then you get a reaction between the carboxylic acid of one and the amino group of the other. That's known as a dehydration synthesis because you pull out water here and they bond together. This is not an acid-base reaction. It's a bit more dramatic than that, but this is the formation of the peptide bond. So you get amino acids linking together in this way to form proteins. So these acid-base interactions can be significant, and those R groups on the side of these peptides, those are what give proteins their functionality. What side chain goes where can have a big difference, make a big difference, have a big impact on how the protein functions, how it folds or doesn't fold, and what sorts of things it can do. Now I'd like you to ponder for a moment, what do you have after you neutralize something? Okay, when you mix an acid and a base, you're going to get a salt and usually water. But will that salt be acidic, basic, or neither? Okay. Obviously, we're talking about conjugates here. Okay, so a strong acid plus a strong base, it's going to be neither acidic nor basic. Strong acid and a weak base, it's going to be an acid. Weak acid and a strong base is a base. Weak acid and a weak base, well, that depends. Why is that? Well, a strong acid and a strong base, neither of those have conjugates. It's just salt and water. There's no acidic or basic function left after those two have reacted. But a strong acid and a weak base, the weak base is going to produce a conjugate acid. So the resulting salt is going to be a weak acid itself. So after the neutralization, you're going to have an acidic solution. Similarly, a weak acid and a strong base, you're going to get a conjugate base as a product. So you're going to have a basic solution. As for a weak acid and a weak base, well, you're going to get a conjugate acid and a conjugate base as products. Okay, so you're going to have, so mixing an acid and a base, the result is going to be a different acid and a different base. And they're each going to have their own equilibrium constant, a Ka and a Kb. And which one it dominates depends just on which one is bigger. If Ka is bigger, then you have an acidic solution. If Kb is bigger, you have a basic solution. The point, there's a lot of points here, but you should remember, once you're done reacting things, the chemicals haven't gone away. You're still going to have products and so on. And in this case, after a neutralization reaction, you might still have an acidic or basic solution. You should never assume it's going to be neutral. And just be aware that the products you make might themselves have their own reactive properties. And moving on, we have the polyprotic acids. This shouldn't be too much of a shock for most of you. Poly just means many, proton, ic. Okay, we're just acids with multiple acidic protons. Okay, there's nothing too fancy there. You should already be familiar with these, I hope. H3PO4, H2SO4, H2CO3. There are lots of polyprotic acids. They're mostly the oxy acids, but those aren't the only ones. The biggest thing to get out of this, to remember, is that a polyprotic acid has multiple Kas, and thus it can have multiple dissociations. And when you put it in solution, it doesn't necessarily stop at just the one. H2SO4 is a strong acid because its first Ka is too large to be measured in water. Its second Ka is still fairly significant. So sulfuric acid, there's a reason we don't use it for the most part in our reactions, because it's more acidic than an equivalent concentration of HCl would be. Polyprotic acids can be useful. They definitely have their uses, but we tend to prefer the monoprotic acids just because they're easier to control than the polyprotic acids. And that's all we really need to say about the polyprotic acids. And you can't really say too much about buffers. A buffer is a solution that resists a change in pH because it's a weak acid or a weak base. It's in equilibrium. And Le Chatelier's principle says that any change you try to make to a system in equilibrium it's going to resist that change. Buffers are incredibly useful and common. Most of the systems in your body are regulated by buffers because you get too far outside of a certain pH range and proteins lose their function. And if your proteins lose their function, you die. So your body is very careful about maintaining pH ranges, and it uses buffers for that. We also use buffers in organic chemistry and various other processes because we need to maintain pH there as well for optimal reaction conditions. It's possible to talk about buffers outside of the context of pH, but we often are talking about pH when we're talking about buffers. But let's go ahead and move on to math problems, because those are big deal. They show up all the time. Let's look at the Henderson-Hasselbach equation. So the Henderson-Hasselbach is a handy shortcut for working out the pH of a buffer. Now, a buffer is the mixture of any weak acid or base and its conjugate acid or base. So if you don't have a buffer, if there's no conjugate, then you're not talking Henderson-Hasselbach, and you'll need to use a nice table. But if you do have both, you're talking Henderson-Hasselbach. And here is the Henderson-Hasselbach equation. You start with your equilibrium expression. Ka equals the concentration of H plus times concentration of A minus over concentration of HA. This derivation works out the exact same way for weak bases, but I'm only going to show you one because this takes up a lot of room. All right, so next we take the negative log of both sides of the equation. That gives us pKa equals negative log of H plus times H minus over HA. So we use the magic of logs to split that up, not entirely, but we split it up a bit, into pKa equals the negative log of H plus minus the log of A minus over HA. Now remember that pH is the negative log of H plus, so that gives us pKa equals pH minus log of A minus over HA. And then we just add that log expression to both sides, and that gives us the Henderson-Hasselbach equation. pH equals pKa plus log of A minus over HA. And we also get, by the exact same derivation, the form of the Henderson-Hasselbach for weak bases. POH equals pKb plus log of B plus over BOH. You could, if you wanted, just go ahead and memorize both of these, or you can look at the more general form, where P, whatever, H or OH, is equal to pK, either A or B, plus log of the conjugate over the weak thing. Just remember that the conjugate's on top, the original weak thing is on bottom. And that is your Henderson-Hasselbach equation. Instead of writing up an ice table every single time you deal with a weak acid or base, you just take a look and see, is this a buffer or not? If it's a buffer, then you can use the Henderson-Hasselbach equation, and that is a fairly quick shortcut, so long as you have the Ka or Kb handy. Now, the Henderson-Hasselbach equation has some interesting consequences, so why don't we go ahead and take a look at no, we won't take a look at those. We'll save those for the next lecture. I've already run over a bit.